Hi, so I have on the board here today a second order homogeneous differential equations quiz, and we're going to be looking at the distinct real roots case, which in a good example that will be the problem on the left. So first I just want to introduce how you go about looking at these second order homogeneous differential equations. Um, wow, that's a lot of words to say. So first of all, let's say in general we have a differential equation in this form. Then what we want to do, so there's kind of the key part to the whole problem is knowing this one fact that a good guess or a good um, starting point is something like this. And the reason for that is because we know if we have an exponential function, just say e to the t, we know the derivative of it is going to be the same thing, right? And then the second derivative is going to be the same thing, and the third derivative is going to be the same thing. So we have a really useful function for a differential equation like this because we can add a coefficient, we can have a constant term here, but we still can maybe form something that can add up to zero. So going with that, with this assumption here that y is going to be of this form, then from that we can take the first and second derivatives. We're going to need that from our equation. So we'll look at the first derivative, and that's going to be RK ERT, just using the chain rule. And then we can look at the second derivative, and that's going to be R squared KERT, again using the chain rule. And once you have that piece, it becomes pretty simple because all we're really going to do is plug these values into our differential equation up top here. So let's just do that. We end up with AR squared KERT plus B RKERT. Oh, you know what I really should do is get the coloring going. Yeah, let's try to do this. I don't usually do this, but we'll try it. Okay, like that. And then we have our C value, which is supposed to be black. So that's going to be CK ERT equals 0. And then the important thing to notice here is just that we have a term in common that we can factor out. So we'll just take out a K ERT and just stick with this coloring. Yeah, sure. And on the inside here, we'll have this whole thing equal to 0. Now, okay, so the key thing here is this is never 0. We want the whole thing to equal 0, but this part's never going to be 0. K can be 0, but that's not interesting because if K is 0, then everything becomes 0, and we just get like the trivial solution of 0. So that doesn't really give us anything because any equation of this form would always have that solution. So we're actually not really, we can almost throw out this piece because it's not going to add anything, and we can just look at this equation here. And the important thing here, the great thing here really is that we have just a quadratic equation that we know how to solve from algebra, just using factoring, quadratic formula, whatever techniques you have for solving a quadratic. But not only that, it is also in the exact same form as the differential equation up here. So we went through all this right now, but what you can do in general is go straight from here, from our differential equation to here. And this piece here is called the characteristic equation or characteristic polynomial that we can just go and take our differential equation and put it into this polynomial and go right to the step and find the roots of this polynomial. Now we have a generic equation here, so we're not going to solve this, but like you'll have your two roots, right? From a quadratic, you're going to have two roots, so we're going to call those roots R1 and R2. And then finally, so we know what our solution looks like. But the last part is that we're gonna, so like a solution, let's call this solution one, using that form is going to be K E R1 T. And then our second solution is going to be K E RT2. But really the way we want to, as our final solution, the way we want to express this, we want to distinguish these two constants, they're different. So we'll write it like this, with two separate arbitrary constants, our two roots, and we add them together because when you take a derivative, if so, we determined that when you plug this in, this piece is gonna be 0, and this piece is gonna be 0. So when you sum your two solutions, you're still at 0. So this is how you want to express. So this would be our solution for this kind of generic differential equation. So now that we like laid all that down, all we want to do is just let's go as an example and work this problem on the left using what we just learned. So we have, just to reiterate, even though you can all see it, but it's sitting right there, but we've got y second derivative 4y prime minus 15y equals 0. And like I mentioned before, we can go straight to the step of turning this right into a quadratic. If you ever kind of forget what you're doing, you can go through the steps we had up here. It's pretty easy to like prove it out again, because you just need really this, you just need to remember that, and then it's easy to get these derivatives and get back to, so you're not just remembering a formula. But that's why you can skip to this step of using a quadratic, to turning it right into a quadratic. So we'll end up with, we'll have here our quadratic. Oh, I don't want to use a y. Let's use r for a root. So 3r squared minus 4r minus 15 equals 0. And so you can solve this by any method you want. I think what I'm going to do, yeah, let's use the quadratic formula. So we get minus b plus or minus b squared, which is going to be 16, minus 4a, which is 3, c minus 15, all over 2a, which is going to be 6. Then this can reduce to 2/3. What is this big thing? So that's going to be 180. This here is going to be 180 over here. That's 180. And then that's a plus sign. So we're going to end up with the square root of 196. But the square root of 196 is just 14. Let's just write this as 4/6. And so over here, we got a plus or minus, so we're going to have two roots, 18 over 6 and minus 10 over 6. And so let's just, but this is just 3. And this is minus 5/3. So we've got our R1 equals 3. R2 equals minus 5/3. And let's put it in that form that I mentioned to get, we defined up here, we defined what we want our y to look like, and that we can sum, we get our two solutions, our two particular solutions, which we can sum together for our forgetting the word that we use for the complete solution. It's a particular solution, and there's the, I forgot the word, so let's not worry about it. It's not that important. I mean, it'd be nice, but it's not that important. Okay, so we have y equals c1 e to the 3, 2 plus c2 equals e to the minus 5/3 t. That will be our solution. There's no there's no initial values, so if you had initial values, you could then solve for these constants, but we don't have that here. Let's just check the answer. Looks like this first one here. And that's correct. So in the video description, I'm going to provide a link to this quiz so you can do some practice problems. And then if you flip through here, you'll see that we have the other cases, the complex case, the repeat roots. And I'm going to go through I'm going to do 2 more videos to cover those cases. But also, if you want to read up, I cover a lot of what we did in this video in the first part here in the method of solving, but then I also have a little bit on the complex case and the repeat solutions here. Also, we have the differential equations cheat sheet, which is not quite complete yet, but it's definitely not complete, but it has some information there if you want to use that, check it out, and that might help a little bit as well. So I'll stop it there, and again, we'll provide a link to the quiz in the description. Thanks.